Here's a sea glider which is from recent deployment around the Faroes. The Faroes on the beautiful ridge that is around you here, and there's the Faroes Plateau. This is a track of a sea glider, which you'll see in a minute now, pulled out like a ribbon to show you the temperatures of the ocean, and there are lots of other variables, but this is the most easy to grasp. In June to August of 2007, we navigated the sea glider through the Faroe Bank Channel, encountering the deep overflow waters, the cold blue colors, and these are flowing out of the Arctic into the warmer Atlantic and being replaced by these warm northward flowing waters on the top. You recall we turned right and just do that once again. Well, it didn't come up, but we turned right and then crossed the Iceland-Faroe Ridge, and this is the front, which Chalmar was talking about this morning, and as an example, the front holding back the cold Arctic waters, which are sliding over the ridge in a narrow 25 to 50 meter thick layer, and but then for biology and fishing interests, this is an interesting structure here. And if we look at that from a satellite, it's located north of the ridge, where that front surface is. This is from a satellite view between Iceland and Faroes. And along this track here, where my pointer is pointing, you do a cross-section and you see that sloping front, again, in temperature and salinity. So if you're interested in biological distributions which rely on fronts, you can see the location problems which ask you to do subsurface sampling in great detail. And when we've done that, in this case in August of 2007, we can see biological activity, phytoplankton growth in the top of the water column here. We can see the front in huge detail. We're actually seeing the glider track here as a sawtooth. This is the sloping density front running from south to north over 250 kilometers of the ridge, and other variables like salinity. But you see the fabric and texture of this beautiful ocean is very extreme, and it really matters. It's not just detail that you could sweep under the carpet. So we can visualize an operational network of sea gliders run from the Faroes, exploiting the connections between physical climate and ecosystems. This would synthesize local and distant climate and fishery goals. And if I've got, do I have 5 more minutes? Back in the Labrador Sea, in a 2-year program in a little earlier in time, we established, using the good offices of the Naturinstitute in Nuuk, and particularly of Heli Sigstad, we established a strong connection between the melting of ice water, the melting ice water from the Arctic, which flows down the sides of Greenland, and we established the connection of that with the major primary productivity of the region. It was a great feeling of joy to me to see this all happen. So now we're looking at the northern Atlantic from space, seeing biological activity in the form of ocean color. Of course, it's false color here, but the reds and greens are phytoplankton growth regions, chlorophyll in some sense, and hot spots of biological growth in the spring, early spring of 2005. And this particular site in West Greenland here is a major region of primary production. And as we zoom in on it, you can see that you wonder why it's there. And biologists were not able to tell me why it was there. And so it just happened that we ran our sea gliders right through that patch, the very patch you see there. And we measured the temperatures and salinities as we went. There are 2 sea gliders tracks right here, following through here, and Chalmar has led the analysis of that data and produced a complete story of this Arctic water being swept like a blanket over the top of the Labrador Sea, controlling the physics of the circulation and also controlling and setting the sites of biological productivity. So we're delighted. We think we did a little something in the service of ecosystems with our physical robotic undersea instruments. Well, that's to sum up what I've been trying to say, the robotic sea gliders produced, we think, significant discoveries at the heart of the global warming climate problem, but it's only done so through a network of collaboration through Seattle, Nuuk, Faroes, and Bergen. And this has many dimensions which you can imagine, including the WUN network, World Universities Network, which has generously funded exchange of our students and some of our faculty interactions. And these are the science items that I've just been through: thin layers of melted Arctic ice water, flooding over the top of the Labrador Sea, controlling deep convection, and these same buoyant waters trapping ocean phytoplankton in the sunlit surface layer, producing the strongest spring bloom of the western subpolar Atlantic. And then closer to home, glider measurements of velocity deep in the sea near Faroes are helping to pinpoint where the cascading Arctic waters suddenly adapt and mix to form the deep waters of the entire world's oceans. We think we have a new way to do that, which has been discovered in the last 6 months. We're building a climatology of the deep, cold Arctic waters cascading over the ridge between Iceland and Faroes, so far with 11,000 profiles through the full depth of the ocean. That number, 11,000, probably equals all of the previous historical data ever taken in the region. So global warming is the tip of the iceberg of global change. Climate, it starts with climate, but it goes to biosphere, energy, economies, environment, and you would probably say unrest, poverty, and warfare if you wanted to really follow Al Gore as he has very correctly made that connection. While we may not mobilize the world over global warming alone, if we begin to attack this problem, then our trajectory of solutions will automatically serve the rest through conservation, self-sufficiency, innovative green-collar technologies. The exponential curves that express all the branches of global climate change are maturing so quickly now that urgent response is needed. And we do have many of the necessary technologies, but they have to be networked across the Arctic Rim. Thank you.
Thank you very much, Professor Rhines. I think we can allow 1 or 2 questions. Are there any questions from the audience? Yes, please. Could you introduce yourself? Please?
Mm-hmm. That was, you see, it was from 16th of August to the 30th. It was 2 weeks. Whoops, I lost it. That was a 2-week profile to do that. So these move slowly, and if I went back to the Argo Float network, there were 3,000 of them, and I took all but 3 of them away. That's about our status now, or 3 or 4. And so what Chalmer and I and Boje Hansen have talked about is how efficient it would be to have perhaps 10 or 20 or 30 of these sea gliders in the northeastern Atlantic, because then, with that, despite the slowness, we would be able to map many of these structures. The vehicle is kind of a Swiss Army knife of instruments in the sense that it can do many things. It can sit and imitate a mooring, just going up and down. It can acoustically be a mailman, a postman, and interrogate deep sea instruments that are lying on the seafloor and suck the information out of them. It can, in a new version by Craig Lee of Seattle, it can go under the ice and navigate far under the ice. So we see it as a versatile instrument for the future.
Okay, thank you very much. I think we'll go for the next speaker.